So, 3i Atlas has now passed its closest approach to Earth, and in the days immediately following that encounter, scientists released a set of new calculations that quietly changed how we understand this object. These updates focus on something surprisingly fundamental: the actual size of 3y Atlas. What makes this noteworthy is that the new size estimates do not simply refine earlier numbers. They directly contradict measurements that scientists have been confident in for months. On December 23rd, researchers published updated calculations that re-examined the object's size using a method based on non-gravitational acceleration. This refers to the very slight push a comet experiences when gas escapes from its surface. As ice sublimates and jets of material stream outward, the object experiences a small rocket-like force that subtly alters its motion. For 3y Atlas, this non-gravitational acceleration was measured at approximately 89.3 times 10 to the negative 9 astronomical units per day squared. Translated into more intuitive terms, this means the object speeds up by about 13 kilometers per day every day. That number may sound dramatic, but in physical terms, it is extraordinarily small. It amounts to roughly 1/5 millionth of Earth's gravitational acceleration. Despite how tiny this effect is, modern astronomy is precise enough to detect it. By combining measurements from hundreds of observatories across the world, scientists can track an object's position with astonishing accuracy, sensitive enough to detect even this minute push. So how does acceleration tell us the size of a comet? The strength of this rocket effect depends on two measurable factors: how much material is escaping from the surface per second, how fast that material is being ejected. Both of these quantities were measured directly by the James Webb Space Telescope. According to those observations, gas is leaving the surface of 3i Atlas at roughly 1,600 kilometers per hour, with a total mass loss rate of about 150 kilograms per second. Once those values are known, scientists can ask a critical question: what size object would produce this exact amount of acceleration given that level of outgassing? When the math is worked through, assuming standard comet properties, the answer comes out to a diameter of roughly 1 kilometer, with an estimated range between 800 and 1,000 meters. This calculation also relies on another important assumption: density. Most known comets are not solid rock. They tend to be loosely packed, porous bodies composed of ice, dust, and voids, with a typical density around 500 kilograms per cubic meter, about half the density of water. Using that standard density, the resulting mass of 3y Atlas comes out to approximately 260 billion kilograms. So according to the December calculations, diameter, approximately 1 kilometer, mass, approximately 260 billion kilograms. That is, what 3y Atlas appears to be based purely on its measured acceleration and outgassing behavior. However, this is where the story becomes complicated. Earlier in the year, between May and September, a different set of observations told a very different story. During that 5-month period, 3i Atlas was tracked by over 230 observatories worldwide. Its position was measured with an accuracy of roughly 0.028 arcseconds, precision comparable to spotting a coin from over 100 kilometers away. Across that entire time span, researchers detected no measurable non-gravitational acceleration at all. This is important because the detection threshold during that period was actually far more sensitive than the recent measurements, roughly 300 times more sensitive. In other words, if even a very small rocket effect had been present during those months, the instruments should have detected it. They did not. This leads to a striking implication. If the acceleration was truly below detection limits earlier in the year, then the object must have been much more massive at that time. A larger mass would naturally respond less to the same amount of outgassing force. Using that logic, Harvard astrophysicist Avi Loeb previously calculated that if the acceleration remained undetectable, the mass of 3I Atlas would need to be at least 33 trillion kilograms. That is over 120 times heavier than the December estimate. At typical comet density, that mass corresponds to a diameter of around 5 kilometers, which matches the size estimate scientists had been reporting for months. So now we are faced with a clear contradiction. Recent acceleration-based calculations suggest a 1-kilometer object weighing 260 billion kilograms. Earlier detection limits imply a minimum size of 5 kilometers and mass of 33 trillion kilograms. That is a 5-fold difference in size and more than a 100-fold difference in mass. So what could explain such a discrepancy? There are several scientifically reasonable possibilities. First, the acceleration measurements themselves are still being refined. Since the earliest papers were released, NASA and collaborating teams have repeatedly revised the non-gravitational acceleration values as they improved their models and corrected for observational uncertainties. If the true acceleration is lower than the initial estimates used in December, then the calculated diameter would naturally increase, narrowing the gap between the 1-kilometer and 5-kilometer scenarios. Second, mass loss over time may be playing a significant role. Between May and September, 3Y Atlas was still far from the Sun and relatively cold. As it approached perihelion later in the year, solar heating intensified dramatically. During that period, the object likely lost billions of kilograms of ice and dust. If the comet was significantly more massive earlier in the year, the lack of detectable acceleration at that time becomes easier to understand. Third, asymmetric outgassing combined with rotation could alter how acceleration appears in tracking data. If active jets are concentrated on one side of the object, the resulting thrust may be directed sideways rather than along the orbital path. In that case, acceleration would not show up clearly in position measurements, even if strong outgassing were occurring. As the comet rotates and its orientation changes, those same jets could later produce measurable acceleration in a detectable direction. This behavior is well documented in comets within our own solar system. Finally, there are the assumptions within the models themselves. The calculations assume a particular density, internal structure, and degree of symmetry in outgassing. Small deviations from those assumptions, slightly higher density, different porosity, or strongly uneven jet activity, can significantly affect size estimates. When those uncertainties are taken into account, the 1-kilometer and 5 kilometers values may not be as irreconcilable as they initially appear. They could converge somewhere in between. The broader point is that this is an active and ongoing area of research. New observations are arriving. Orbital solutions are being refined. Acceleration models are being updated. This is how science normally progresses, especially when studying something genuinely unfamiliar. What makes 3I Atlas especially challenging is that it is interstellar. We have never observed a comet from another star system with this level of detail before. Its chemistry, internal structure, and thermal history may differ substantially from objects formed in our own solar system. Some of the assumptions that work well for familiar comets may not apply perfectly here. In many ways, scientists are learning in real time how to interpret data from an object that formed billions of years ago in a completely different stellar environment. And that is what makes this moment quietly fascinating. If you have thoughts or theories about what might be happening with 3I Atlas, feel free to share them in the comments. If you found this exploration calming, informative, or intriguing, please consider liking the video and subscribing for more slow, sleep-friendly space documentaries. God bless you, and I wish you a peaceful and restful night.